Stephen Hawking wasn't just a physicist. He was a visionary who peered into the universe's deepest mysteries. Despite being confined to a wheelchair and speaking through a computer, his mind soared beyond galaxies, beyond black holes, beyond time itself. What made Hawking extraordinary wasn't just his resilience in the face of ALS, but his ability to translate complex cosmic principles into wisdom about our very existence. Today, we explore one of Hawking's most profound insights, that energy never truly dies. And through this fundamental law of physics, we might glimpse something remarkable about ourselves, about consciousness, about what happens when our physical bodies cease to function. Hawking often said, "The universe doesn't allow perfection." Yet, the perfect symmetry of energy conservation seems to be an exception. The first law of thermodynamics tells us energy cannot be created or destroyed, only transformed. This universal constant became Hawking's pathway to contemplating humanity's greatest mystery. What happens after death? In the coming chapters, we'll journey through quantum mechanics, consciousness theory, and the physics of information. We'll explore how Hawking's brilliant insights might offer a scientific framework for understanding consciousness beyond the physical body, not as supernatural fantasy, but as a natural consequence of the laws that govern our universe. When you look at a flame, you're witnessing energy changing form, chemical energy becoming heat and light. When lightning strikes, electrical potential transforms into thunder and brilliance. Every transformation we witness follows the first law of thermodynamics. Energy changes form but never disappears. Hawking was fascinated by this conservation principle, especially as it applied to information and quantum states. In 1974, he discovered that black holes emit radiation, now called Hawking radiation. This breakthrough suggested that even black holes, once thought to destroy information completely, actually preserve it at the quantum level. The implications are staggering. If energy and information cannot be destroyed even by the most destructive forces in the universe, what does this mean for the information patterns that comprise our thoughts, memories, and consciousness? Hawking proposed that reality might be understood as information encoded on the boundaries of space, like a cosmic hologram. This holographic principle suggests our three-dimensional reality might be projected from information stored on two-dimensional surfaces. Information is not lost, but it's not returned in a useful way, Hawking once explained. It's like burning an encyclopedia. The information isn't lost if you keep all the smoke and ashes, but it's difficult to read. This principle raises profound questions. If the universe preserves information at its most fundamental level, could the intricate patterns of our consciousness, the most complex information structure we know, somehow persist after physical death? The answer may depend on understanding what consciousness actually is. What exactly is consciousness? This question fascinated Hawking throughout his life. Classical neuroscience tells us consciousness emerges from neural activity, essentially an extremely complex computer made of biological tissue. But quantum physics, which Hawking helped shape, suggests something far more mysterious. Roger Penrose, who worked with Hawking on black hole theories, proposed that consciousness might involve quantum processes in brain microtubules, cellular structures that could potentially sustain quantum coherence. These quantum effects could theoretically create a field of consciousness not entirely bound by classical physics. Hawking initially questioned this theory, but later acknowledged that quantum mechanics might indeed play a role in consciousness. The brain's approximately 86 billion neurons create more possible connection patterns than there are atoms in the observable universe. This astronomical complexity might allow for quantum effects that we don't yet fully understand. If consciousness involves quantum processes, operating at scales where particles can exist in multiple states simultaneously or remain entangled across vast distances, then consciousness might not be entirely localized within the physical brain. Instead, it might interact with fundamental fields that permeate reality itself. As Hawking explained, quantum effects typically involve isolated systems of a few particles. But the brain is warm, wet, and noisy, seemingly the worst environment for quantum mechanics. Yet, evolution may have found ways to harness quantum mechanisms. This perspective aligns with Hawking's later thinking on information theory, that information, including the information patterns of consciousness, is more fundamental than the physical substrate that temporarily holds it. Black holes represented Hawking's greatest intellectual battleground. Initially, his calculations suggested black holes completely destroy information, violating quantum mechanics' principle that information cannot be lost. This information paradox troubled Hawking for decades. In 2004, he dramatically reversed his position, conceding that information must somehow be preserved. His solution: information might be encoded on the boundary of black holes, their event horizons, rather than being destroyed inside. This resolution parallels questions about consciousness after death. If even black holes, cosmic vacuum cleaners with gravity so strong light cannot escape, cannot truly destroy information, what happens to the incredibly complex information patterns that constitute your consciousness? Hawking's mathematics suggested information might be scrambled beyond practical recovery, but never truly lost. Applied to consciousness, this could mean that while the coherent you dissolves after death, the information pattern isn't eliminated from the universe. Black holes ain't as black as they are painted, Hawking famously quipped. They are not the eternal prisons they were once thought. Similarly, perhaps death isn't the absolute end it appears to be from our classical perspective. If information cannot be destroyed, but only transformed, then consciousness, whether purely classical or partly quantum, might undergo transformation rather than extinction. This isn't mysticism, it's a logical extension of physical principles Hawking helped establish. The same mathematics that preserves information at a black hole's boundary might apply to consciousness at life's boundary. One of Hawking's most mind-bending contributions came from applying holographic principles to cosmology. He suggested that all the information contained within our universe might actually be encoded on its boundary, like a two-dimensional surface projecting a three-dimensional reality. This isn't just abstract theory, it helps resolve mathematical contradictions in black hole physics and quantum gravity. If reality functions holographically, then information exists non-locally. The information isn't just in one place, it's fundamentally spread across dimensional boundaries. What might this mean for consciousness? Neuroscience already shows consciousness isn't localized to any single brain region but emerges from interconnected networks. The holographic principle suggests this non-locality might extend even further. Consciousness could be encoded in fields that transcend the physical brain while interacting with it. Physicist David Bohm, whose work Hawking respected, proposed that consciousness might function like a hologram, where each part contains information about the whole. This holonomic brain theory suggests conscious experiences aren't stored in specific neurons, but distributed throughout brain wave patterns that interface with deeper quantum fields. The human mind is not limited by its physical components, Hawking once reflected. Like software isn't limited by the hardware it runs on. If consciousness operates holographically, interfacing with fundamental fields that exist beyond local spacetime, then physical death might not end consciousness but transform how it's expressed, changing the interface rather than erasing the information. What exactly is a memory? Neuroscience tells us memories form when neurons create specific connection patterns. But Hawking encouraged us to think deeper. Memory is fundamentally information, and information is physical according to modern physics. Information isn't abstract, it's encoded in physical states, whether neural connections, magnetic orientations on hard drives, or quantum states. And physics tells us information cannot be destroyed. When you delete a file from your computer, the information isn't truly gone. It's just no longer organized in a readable pattern. Similarly, when brain cells containing memories die, the information they encoded doesn't vanish from the universe, it transforms. But transformed into what? This is where Hawking's work on quantum information becomes relevant. Quantum information theory, a field Hawking helped pioneer, suggests information might be preserved in ways classical physics cannot explain. Just as quantum particles can exist in multiple states simultaneously, superposition, or maintain instant connections regardless of distance, entanglement, quantum information might transcend its physical medium. Hawking proposed that information might be more fundamental than the matter encoding it, a radical reversal of traditional thinking. If true, then the information patterns comprising memories and consciousness might persist in quantum fields even after their physical substrate degrades. Information has a different kind of physics, Hawking noted. It can be transformed, compressed, or encrypted, but never destroyed. This perspective suggests a profound possibility. What we experience as consciousness might be the interface between classical brain function and more fundamental quantum information fields that don't disappear when the brain dies. When we think about Stephen Hawking's life, we witness a powerful testament to consciousness transcending physical limitations. Despite losing control of most bodily functions, his consciousness, his self, remained intact, adapting to communicate through increasingly minimal physical channels. This practical example illustrates a profound principle. Consciousness demonstrates remarkable independence from physical constraints. Hawking ultimately communicated using just facial muscle movements, yet his consciousness remained undiminished. This suggests consciousness might be more like a field interacting with physical structures than generated by them. Quantum field theory, a cornerstone of Hawking's work, proposes that fundamental forces and particles are excitations in underlying fields that permeate all space-time. What if consciousness similarly represents excitations in a fundamental field, not generated by brains but temporarily localized through them? This would align with the conservation principles Hawking championed. Energy doesn't disappear at death, it changes form. Information isn't lost, it transforms. Could consciousness similarly change expression rather than cease to exist? The brain is essentially a computer and consciousness is a program, Hawking once said. But he later refined this view. It's not just any program. It's one that evolves, writes its own code, and might even survive its hardware. If consciousness functions like a field pattern rather than merely a computational output, physical death might represent a phase transition, like water becoming steam, rather than annihilation. The pattern changes expression but preserves its information content across the transformation. There ought to be something very special about the boundary conditions of the universe. And what can be more special than that there is no boundary? No discussion of Hawking's legacy would be complete without exploring his contributions to multiverse theory. Hawking proposed that our universe might be just one of many, perhaps infinite universes, constantly branching from quantum events. In this framework, consciousness might express across multiple universe branches simultaneously. The you experiencing this moment represents just one branch of possibilities. In quantum many-worlds interpretation, which Hawking considered seriously, all possible quantum states actually occur in different branches of reality. This opens remarkable possibilities for understanding consciousness beyond death. If consciousness involves quantum processes, as growing evidence suggests, then physical death in one universe branch wouldn't necessarily terminate consciousness across all branches. The information pattern might continue to evolve along different trajectories. More radically, Hawking suggested quantum effects might allow information to tunnel between different regions of the multiverse. Applied to consciousness, this suggests the information patterns constituting you might transition to different expressions rather than disappear at death. The universe is governed by science, Hawking said, but science tells us that we can't predict the future with certainty because the universe has multiple possible futures. This multiverse perspective offers a scientifically grounded framework for consciousness continuity that doesn't require traditional religious concepts of souls or afterlives. Instead, it suggests consciousness might naturally extend beyond any single physical manifestation through fundamental quantum processes. We are just an advanced breed of monkeys on a minor planet of a very average star. But we can understand the universe. That makes us something very special. Throughout his extraordinary life, Stephen Hawking warned us about many things: climate change, artificial intelligence risks, nuclear proliferation. But perhaps his most profound warning was also his greatest source of hope. We must expand our understanding of consciousness and reality beyond classical limitations. Hawking recognized that viewing consciousness as merely a temporary computation in an isolated brain creates existential despair. If we're nothing but brief computational accidents in an indifferent universe, why strive for anything beyond immediate gratification? But his work on energy conservation, information preservation, quantum effects, and multiverses points toward a different conclusion. Consciousness might be far more fundamental, persistent, and interconnected than we've imagined. This isn't idle speculation or wishful thinking. It's the logical extension of physics Hawking helped establish. The same principles preserving information at black hole boundaries might preserve the information patterns of consciousness across physical transitions. Remember to look up at the stars and not down at your feet, Hawking advised. Perhaps in those stars and the quantum fields connecting them, aspects of our consciousness already exist in ways we're only beginning to understand. The revolution Hawking sparked isn't complete, but his work offers a framework where consciousness need not be extinguished at death, a framework grounded in physics rather than faith. As quantum biology and consciousness studies advance, we may discover scientific evidence for what intuition has long suggested, that we are more than temporary patterns in isolated brains. Hawking's final warning is this: don't confuse current scientific limitations with ultimate boundaries of possibility. The same equations suggesting energy and information persist might one day formally demonstrate that consciousness, in some form, continues as well.